Let's just dive right into this explainer, shall we? Today, we're unpacking the foundational principles of how our digital world actually organizes and retrieves, well, literally colossal amounts of data. Think about it. Every single time you log into a website, check your bank balance, or just stream a movie, there is this massive, hidden architecture working tirelessly behind the scenes to make it happen in milliseconds. So let's pull back the curtain on that invisible world. How does the modern world remember everything? I mean, the sheer scale of that question is mind-boggling. We are generating massive amounts of data every single day, right? But here's the thing. Without a reliable system, all that data is really just noise. Imagine walking into a library holding millions of books, but there's no index, absolutely no shelves, and zero categorization. It'd be entirely useless. The whole evolution of human computing is really just the evolution of us trying to figure out how to remember, store, and access information efficiently. And to figure that out, we're drawing our insights directly from the comprehensive textbook, Databases and Their Security. Now, this book gives us a seriously detailed look into the theory, the history, and the practical application of data systems. But don't worry, we're going to take all that dense academic theory and break it down into a fast-paced, highly visual journey for you. Here is our roadmap for today. First up, the evolution of data management systems. Second, the architecture of modern databases. Third, design and data normalization. And finally, the basics of the SQL query language. Section 1. Evolution of Data Management Systems. Let's take a quick look back in history. You really can't appreciate where we are today without seeing just how incredibly labor-intensive this all used to be. I mean, look at this progression. We leap from tracking royal treasuries by hand on Sumerian clay tablets way back in 4000 BC to using punch cards in the 1800s for automating looms and tallying census data. Then, flash forward to 1951, and you've got the UNIVAC 1, literally a 13-ton computer running on magnetic tapes. But the real game changer? That hit in the 1970s when Edgar Codd at IBM proposed the relational database model. Suddenly, we had a unified way to navigate and manipulate data without having to write completely new programs for every single question we wanted to ask. It absolutely revolutionized things, paving the way for stuff like XML for web data in the late 90s. Section 2. Architecture of Modern Databases. Moving away from the history books, let's examine the actual skeleton of a modern system. Okay, so the crucial takeaway here is that early file systems were incredibly fragile. They suffered from strict data dependence and honestly pretty weak security. Back in the day, every single software program had to know exactly where its data was sitting on a physical tape. If someone swapped that tape, boom, the program completely broke. Plus, if two people tried to open a file at the exact same time, it was total chaos. Modern database management systems, or DBMS, fix all of that. They act like this ultra-powerful middleman that handles all the security, manages who gets access, and ensures safe, concurrent updates without everything crashing. Now, think of the ANSI-SPARC architecture, which was proposed way back in 1975, as this brilliant three-level framework. It essentially guarantees that if a physical hard drive changes, the end user never even notices. It splits the database into 3 layers. The external level is just what you, the user, see right there on your screen. The conceptual level is kind of like the master logical blueprint of all the data. And the internal level? That's how the data is physically stored on the actual server. Because these layers are totally separated, an IT admin can completely swap out a server's hard drive at the internal level, and your external view remains completely uninterrupted. Pretty neat, right? Taking this a step further, let's look at how systems talk to each other. In a basic client-server setup, your computer's basically doing a lot of the heavy lifting. But a 3-tier architecture adds a middleman, an application server. This makes it absolutely perfect for web browsers. Instead of your computer working overtime, you just use a thin client like Google Chrome or Safari. Your browser talks to that application server in the middle, and then that server talks to the database. This little tweak is exactly what makes scaling massive web applications so secure and lightning fast today. Moving on to Section 3, Design and Data Normalization, Organizing the Chaos. Because look, throwing all your information into one giant table is just a massive recipe for disaster. Take a look at this incredibly messy table. You've got 2 employees, Ivanov and Petrov, and they're both sitting in room 17. The phone number 123 is listed right next to Ivanov, but there's a blank next to Petrov. Now what happens if that room gets a new phone number? You'd have to hunt down every single employee assigned to room 17 and update their specific row. If you miss even one person, your data is officially corrupted. In the biz, we call that a massive update anomaly. So how do we fix it? Well, we use a step-by-step process called normalization to break apart these clunky blocks of text into sleek, interconnected tables. This is really the beating heart of relational database design. Step 1, first normal form, basically means breaking things down into their smallest possible parts, like splitting a full name into separate first, middle, and last name columns. Then, second and third normal forms are really all about making sure that every single piece of data in a table depends entirely, and I mean absolutely exclusively, on that table's primary key. If a piece of data actually belongs to a different concept, we slice it right out and give it its own table. So by splitting that messy data we saw earlier, our first newly cleaned up table now only focuses on which employee sits in which room. Notice how we've completely ripped the phone numbers out of this view. Now this specific table has one job, and one job only, tracking the location of personnel. And then we have this second table, which simply maps the room to the phone number. Think about what this means. If the phone number for that room changes tomorrow, we literally only have to update it in one single place. We then use relationships to link this second table back to the employee table based on the room number. And just like that, boom, we've completely cured our update anomaly and perfectly optimized our storage. Section 4, Basics of the SQL Query Language. Let's talk about communicating with databases. Now that our digital house is designed and beautifully organized, we need to learn the language to actually talk to it. SQL, or Structured Query Language, acts as the universal translator between us humans and the machine. Whether a company is running MySQL, PostgreSQL, or Oracle, SQL is the foundational standard across the board. And honestly, what makes SQL so incredibly brilliant is that it's a non-procedural language. That means you literally just tell the database what you want, and the database's internal engine does the heavy lifting to figure out how to go get it for you. To break it down simply, you've got two main types of commands. DDL, or Data Definition Language, is essentially like building the house and setting up the rooms. You use the create command to pour the foundation of a table, laying out the columns and data types. Once the physical table actually exists, you switch over to DML, or Data Manipulation Language. This is basically just moving the furniture around inside the house. You use insert to drop new records in, update to tweak them, or delete to completely toss them out. But when you actually want to find specific information, say looking up all the students in a specific major, the select command is going to be your absolute best friend. It's truly the most powerful command in your entire SQL arsenal. You can pair it with where to filter down exactly who you're looking for, use group by to quickly count how many students are in that major, and then slap on an order by to sort the whole list alphabetically. Our source text actually gives us a really great practical example of this in action. By querying the system to connect a student table with a hobbies table, we instantly get this unified view. We can see right away that Polish Shook likes computers and boxing, while Cherniak is into computers and skating. The database seamlessly joins all this data across the multiple tables we set up earlier, returning exactly what we asked for. But hold on, what if we want to pull a list that includes students who haven't listed any hobbies at all? A standard inner join would actually filter them out completely because it only shows records that have a perfect match in both tables. If we want a full, complete roster of students regardless of their extracurriculars, that is exactly why we use a left join. It literally forces the database to bring in absolutely everything from our primary student table on the left and just match it up with whatever hobby data it can find on the right. See what happens here? Notice how the student Sankov now successfully appears in our results, even though he has a completely empty hobby field. If we had just run a standard query, Sankov would have been totally invisible to us. Using that left join ensures that absolutely no user profile gets accidentally left behind, keeping our dataset 100% accurate to the original roster. There's a quote from our source material that says, "The effectiveness of an enterprise directly depends on the performance and reliability of its information system, the foundation of which is the database." Honestly, that perfectly hits the nail on the head. Everything we've unpacked today, from the historical evolution of storage capes to the ANSI-SPARC architectural tiers, the strict rules of normalization, and the precise syntax of SQL, it all serves one absolutely crucial goal: building a rock-solid, highly performant foundation. Because if the database is weak, the entire enterprise crumbles. So I want to leave you with a final thought to mull over. Right now, in this exact moment, how is your own personal data being structured, normalized, and queried across the web? As you go about your day navigating the internet, Just think about the primary keys assigning your digital identity, the three-tier architecture securing your passwords, and the incredibly vast SQL queries joining your preferences across servers worldwide. It's a massive, unbelievably complex symphony of structured data running entirely behind the scenes. Thanks for tuning into this explainer, and definitely keep questioning how the digital world works around you.